One of the pleasures of being the president of the Institute of Acoustics is to award medals and certificates for various forms of excellence. And it's my particular pleasure now is to read the citation for the award of the R.W.B. Stephens Medal, which is given for excellence in research and education. And the recipient this year is Raf Orlowski. The citation reads as follows: following a first degree in electrical and electronic engineering at Nottingham University, Raf stayed on to study for a PhD developing an acoustic aid for blind people. He was subsequently appointed as a research associate at Cambridge University, working with Peter Parker and Mike Barron on the development of acoustic scale models for the design of auditoria and other large spaces. A permanent academic position followed as a new blood lecturer at Salford University, where he taught room acoustics and noise control, as well as supervising research work. In 1990, Raf returned to Cambridge to help set up an acoustics consultancy office for Arup, where he worked on a number of prestigious projects, as well as continuing to lecture on acoustics and to supervise research work. He was later appointed as a visiting professor at the University of Sheffield. In 2009, he formed his own acoustics team at Ramboll, working in building acoustics consultancy and continuing with occasional lecturing and research supervision. He was recently appointed as a visiting professor in acoustics at University College London. Raf is one of the few people in the acoustics community who have equal experience in both academe and professional practice, and this has enabled him to make important contributions to both by employing knowledge from one sphere and applying it to the other. In education, Raf has been deeply committed to teaching acoustics to both undergraduates and postgraduates, and has inspired many students to work in the acoustics field, either as engineers or researchers. He has supervised PhD and master's projects, and many of his research assistants have gone on to leading positions in the acoustics field. He has continued this commitment to education while in consultancy by mentoring students and young assistant consultants, helping them to develop their acoustic knowledge. As an acoustics consultant, Raf has applied the results of his research wherever possible in the design of buildings, and has been responsible for the realization of a series of theatres, recital halls and concert halls which have gained good acoustic reputations. He has recently completed a major project at the South Bank Centre in London and continues to advise in the acoustics of the Royal Festival Hall. It's for his dedicated commitment to education and research and his implementation of the fruits of the research into the built environment that the IOA is pleased to award Raf Orlowski the R.W.B. Stephens Medal.
Well, it's a great honour to be awarded the R.W.B. Stephens Medal of the Institute of Acoustics. And in receiving it, I'd like to thank all my colleagues and all the people I've worked with who helped me along the way. And the underlying theme of my lecture is research into practice and practice into research. In essence, it's an account of my experiences both in the academic sector and also in professional practice, where I've been able to make some contributions by employing knowledge from one sphere and using it in the other. I'd like to start with just to touch on my postgraduate work because it has a connection with R.W.B. Stephens and shows what a generous person he was in sharing his knowledge with others and being helpful to researchers. The work was on the development of an acoustic aid for blind people to help with their mobility. My supervisor at Nottingham University, Professor Raymond Burl, had developed a device called the clicker, which was a handheld device which blind people held like a torch, and it emitted a series of audible clicks into the environment in front of the person, and they were able to listen to the reflections from obstacles and so help their mobility. Now, although it was a very successful device in engineering terms, it wasn't favoured by blind people because it drew attention to their disability and was masked to a certain extent by road traffic noise. So my task was to develop an ultrasonic version, pretty much the way bats echolocate their environment. And this is a prototype version which we were testing. The transmitter sends out a series of ultrasonic pulses. The reflections, in this case from the pole, are picked up by two receivers either side of the subject's head, and the signal is presented to the subject as a series of audible clicks, and he is able to tell the distance of the obstacle by the rate of clicking, and he can tell the direction of the obstacle by the interaural difference between the two earpieces in terms of time and intensity. Now, the design of the receiving transducers was quite critical to get this interaural difference correct. And so in developing these, it was deemed necessary to design an anechoic chamber. And a search of the literature didn't reveal much about designs of anechoic chambers at ultrasonic frequencies. We needed it to be operational up to 50 kilohertz. The transducers themselves were working at 40 kilohertz. And my supervisor suggested that I write to the fount of all knowledge on physical acoustics, Dr. R.W.B. Stephens. So I wrote a letter to Dr. Stephens with some trepidation, and I was delighted to receive a lengthy reply from him. This is his reply to me, 1973. And in it, he explained to me the relationship between pressure reflection coefficient and the density of polyurethane foam, which we were using to line the chamber. And he also advised me on the taper angle of the wedges. And you can see the constructed anechoic chamber there on the right. Now, many years later, I received a packet from Linda Canty at the Institute. And inside there was an envelope containing my original letter to R.W.B. Stephens. And on the back of the envelope, Ray Stephens had jotted a little note to himself, and you can see it there. Pressure reflection coefficient will not differ a great deal, and then he thought maybe a great deal sounds a little bit strong. So he crossed it out, it will not differ appreciably for the higher frequencies with change of density. So that was a very nice thing to receive. What a fantastic service the Institute provides for us. This letter apparently dropped out of an old copy of JASA as Linda was sorting out the Institute's library. So thank you very much for that, Linda. I first met Ray Stephens in person at an IOA Spring Conference in Portsmouth in 1987. And I saw that he was intrigued with the number of students that were present at that conference. And I explained to him that I'd introduced an initiative where final year students studying acoustics presented their final year projects to delegates at the Institute to give them practice in presenting papers and also to get feedback from experienced practitioners. And Ray thought it was a great idea and enjoyed chatting with the students. And I still think we should encourage these student sessions at our conferences because it gives the young people a kind of step up on the ladder. Now, when I finished my PhD, I had the honour of being, privilege of being appointed as a research associate to Peter Parkin and Mike Barron at Cambridge University. Both Peter and Mike, incidentally, are Rayleigh Gold medalists of the Institute, and they were working on the development of acoustic scale modelling to help with the design of auditoria. Now, I thought that this is a new area of work and that the skills that I developed during my PhD would not be particularly relevant to this area of work, but very soon I found myself designing and developing ultrasonic loudspeakers with the correct beam width and using them to transmit pulses and looking at the reflections of various obstacles. The main difference being was that the reflections were coming from inside a very large wooden box rather than from lampposts. So these are the sorts of models we were working on, 8-scale models. But our horizons did expand, and we became involved in the design of a concert hall for the London Symphony Orchestra at the Barbican Concert Hall. Now, we had no influence over the design of the hall, but we got involved with it during its completion stages when the acoustic quality of the hall didn't match up to expectations. The design of the Barbican Hall, those of you who've been there will know that it's a very unusual shape for a concert hall. It's very wide at 43 metres compared to the traditional shoebox halls, which are 20 metres. It has a low volume per seat of 8.8 cubic metres, whereas typically it should be 10 to 12 cubic metres. And it has these very deep beams that protrude from the ceiling into the auditorium, 3.7 metres deep. And as we were working on the final stages of the Barbican, this came to the attention of the BBC, who came to visit our laboratory and film work in progress. And that film was shown during the official opening of the hall. It was on BBC Two. The hall was opened by the Queen in 1982. And I'd like to show you a clip from this film because it gives you a very good impression of what the sort of work we were doing in the model and the sort of oralizations we were doing at the time.
Well, the reason for building and testing the model of the concert hall is that it gives us a much better insight into the acoustical quality of the concert hall before the real building is built. And we would get very little of that information if we were just looking at drawings. The unique feature about this concert hall is the ceiling design. Now, for structural reasons, these deep beams had to be enclosed in the volume of the concert hall, and these provide these rather deep recesses in the ceiling, which could provide acoustical problems. There could be late reflections or echoes, and there could be localized reverberation in these recesses. And so some method of breaking the sound up had to be devised, and the architect thought of suspending these plastic spheres from the ceiling, 2,000 of them in 3 different sizes. And we've tested the model with these spheres suspended from the ceiling, and in fact they're very beneficial to the acoustical quality in the concert hall. Well, this is a 1:8 scale acoustic model, and one of the most interesting tests that we do in the model is to play music through the model and then record the music on a little dummy person with 2 microphones, one on either side of his head, and then we listen to these recordings and assess the acoustical quality of the concert hall model in different seats. The music is actually played over 2 loudspeakers placed on the stage, These are rather specialised loudspeakers because they reproduce these very high frequencies that we need in scale modelling. Now, because this is a 1:8 scale model, then the music has to be speeded up 8 times, and the pitch is also increased 8 times, which is 3 octaves. So when the music is actually played through the model, it sounds very squeaky and very fast. I'm now replaying the third movement of Mozart's Jupiter Symphony into the scale model at 8 times normal speed, and this is being recorded by the little 8 scale model person and is coming onto these 2 channels here. When the recording is over, I shall switch it off and rewind it, and then we can listen to the recording at normal speed. The acoustics of the model has now been impressed on the original music, and when we listen to it at slow speed, we'll be able to hear the quality, the acoustical quality of the concert hall. The tape recorder is now running at normal speed, and I'm listening to the acoustics of the model in the first tier of the balcony, which is where I had my little dummy man who was doing the recording for me. The acoustical quality is good. It perhaps needs minor adjustments to slightly lift the bass reverberation time. We're doing adjustments in the real building at the moment, and these will be completed by the time the concert hall opens, and then the conditions should be optimum for the performance of music.
So one of my final statements about the bass reverberation time is can be interpreted as a classical understatement. So the bass reverberation time indeed turned out very low, and it was largely due to the excessive seating absorption. And despite our best efforts to improve the situation and those of others that followed us who tried to improve it, the acoustic quality of the Barbican Hall has never reached a particularly high standard. And when Sir Simon Rattle was appointed as the music director of the London Symphony Orchestra, he made it quite clear that he was dissatisfied with the acoustics of the Barbican Hall, and this led to the initiative, of course, of designing a new concert hall for London, which at this stage, the plans are at a very early stage, and they have yet to raise the £288 million to construct it. Now, although 8-scale models can reproduce sound fields in auditoria with great accuracy, and they're still used today in the most prestigious projects, they're not very useful in terms of the design process, which can often require design decisions to be made fairly quickly. So Mike Barron suggested modelling at 1:50 scale. This is a 1:50 scale model concert hall with a scaled Orlowski. And we looked at developing this technique, and we found that we could make accurate measurements up to the 1 kilohertz octave full scale. And it proved very popular as a design tool. It was quickly adopted by acoustic consultants who used it for the design of St David's Hall in Cardiff and the Theatre Royal in Plymouth. And when I later joined Arup Acoustics, I used it extensively for the design of quite a number of auditoria and also for other large spaces, and I'll talk about that a little bit later on. So, as well as modelling auditoria, we looked at modelling other large spaces, and we focused on factory buildings because they have a rather disproportionate shape. They often have very extensive dimensions in the horizontal plane, but only limited dimensions in the vertical plane, what we sometimes call the pizza box shape. And these sorts of shapes of spaces do not align particularly well with Sabine's theory, so-called non-Sabine spaces. And so we chose a factory manufacturing light bulbs to build a 1:16 scale model. which gave us information up to the 4 kilohertz octave full scale. This is the model that you can see there. And we were able to model sound propagation with distance with good accuracy. And this enabled us to look at optimizing noise control measures. And in this case, we were looking at the effect of suspended absorbers. And we found that by combining suspended absorbers and barriers, we could get noise reductions of up to around 10 dB. Now, after a number of years at Cambridge, I managed to be appointed to a permanent position as a lecturer at Salford, working with Professor Peter Lord. You can see him there in the central picture wearing his traditional white tie. And my jobs at Salford were teaching room acoustics and noise control and also to supervise research work. And I continued to be interested in auditorium acoustics, and I was intrigued by the design of diffusing surfaces. And when I was approached by a young postgraduate student who wanted to do a PhD in auditorium acoustics, I suggested that he do his PhD on the design of diffusing surfaces. That student was Trevor Cox, and he not only wrote a brilliant PhD thesis, he subsequently wrote a book on the subject, and he's now, of course, an authority on the subject. And some of the early diffusing surfaces he was looking at are shown there on the left of that slide. To his colleague Bill Davis, who wanted to do a similar PhD, I suggested finding out an accurate way of measuring the absorption of auditorium seating and validating it. And Bill also wrote a brilliant PhD thesis, and the method he validated is now widely used in the industry for measuring the absorption of auditorium seating. And to a third student at that time, David Waddington, I suggested measuring the acoustical impedance of absorbing surfaces using a 2 microphone technique that you can see there on the right-hand side. I supervised a number of other students as well, but I wanted to particularly mention these 3 because not only did they complete very successful PhDs, but their careers in acoustics have flourished, and they're all now professors of acoustics. And I'm pleased that David is here today chairing some other sessions. Now, I enjoyed teaching and research enormously, but the lure of actually acoustically designing buildings was very tempting, and I was made an offer I couldn't refuse, which was to set up a new consultancy office for Arup Acoustics back in Cambridge. And one of my first projects was the design of a new opera house for Glyndebourne. This was very much a team project, with the original concept acoustic design being done by Derek Sugden, who you can see there, the founder of Arup Acoustics. The execution was carried out by Rob Harris, supported by myself and also others, including Helen Butcher, who I'm pleased is also here at this conference. She was a very important part of that design team. My main responsibilities in the design was to use the scale model in optimizing the shape. We found that it was quite seriously focusing sound, and we needed to neutralize that. So I became involved in designing the diffusing surfaces and also measuring the seating absorption according to the new Bill Davis method. And that's the completed opera house. The light-coloured brown areas are in fact all the diffusing surfaces to counteract the focusing. The Opera House has now been open for about 25 years, and it's got a very high reputation, including the acoustics. We effectively entered an era of auditorium design where the sort of problems that were encountered in the Barbican Concert Hall need no longer occur. Now, as well as working on auditoria, we got involved with quite an extensive project with London Underground in introducing absorption into underground stations to increase speech intelligibility from the public address system. And our original concept in these circular section stations was to introduce an acoustically absorbing pod that was suspended from the ceiling, as you can see on the left-hand side there. We then extensively modelled this concept using 1/16 scale modelling, as you can see in the central image there. And then when we'd optimised it, the concept was actually constructed at full scale and installed in St John's Wood Station, as you can see on the right-hand side there. And we were able to demonstrate a significant increase in speech intelligibility and also a reduction in noise levels. We continued our work for London Underground and also the Mass Transit Corporation in Hong Kong, looking at stations with different cross-sections, rectangular, different shapes and sizes, to draw up guidelines for the acoustic treatment of stations to meet speech transmission index requirements. And at this time I was approached by another postgraduate student. His name is Jan Kang, who I invited to do his PhD in more academic depth, if you like, of looking at these guidelines. He also went on to produce an excellent PhD. His PhD was actually on the sound propagation in long enclosures. He's now written a book on it, and of course he is now also a professor of acoustics. Probably the most complicated station we worked on was the new station for Canary Wharf, which was designed by the architects Foster and Partners. We constructed a 1/50 scale model of it, which was several meters long, and we developed 1/50 scale column loudspeakers so that we could measure the speech transmission accurately over the concourse area. And this enabled us to determine the area of acoustic absorption that was required to meet an STI value of 0.5, which was the target. And the areas of absorption you can see is the black stripes there. And there was also a similar area of absorption on the ceiling. Now, we had a lot of opposition from the architects about installing absorption on the ceiling, because they'd created beautiful concrete wings on the ceiling, and they didn't want this covered up with absorption. But they knew, they were finally convinced they had to meet the target of 0.5 STI, and we did develop a perforated facing with them, which consisted of stainless steel tubes backed by mineral wool. You can see it there on the ceiling, and the overall target was achieved. The design of spaces which focus sound led to some interesting opportunities of applying Trevor Cox's work on diffusing surfaces. So the architects for Recital Hall, for a music school called Benslow Music School, decided they wanted to have a near circular plan shape for the hall, surmounted by a dome. And we advised them very early on that this was going to cause very serious focusing problems, and it really wouldn't be suitable as a recital hall for string quartets and so on. But they were adamant that they wanted to keep this form for the recital hall, but they were prepared to modulate the walls to neutralize the focusing. And so we brought Trevor onto the team, and he used his optimization program for designing diffusers, and we agreed with the architects to use a sinusoidal motif for the modulation, and Trevor put that into his program, and he produced the profile that you can see on the left-hand side. This was the ideal profile for neutralizing the focusing, and it was reproduced perfectly in the construction of the wall that you can see there on the right-hand side. And when the architects saw this, they were absolutely delighted with the aesthetic look of the thing. And we were very pleased because it dealt with the focusing. So there's quite a harmonious outcome there between architects and acousticians. Now, in the 1990s, the Department for Education decided that it wanted to update its guidelines for the acoustic design of schools, and they asked me to progress this, which involved quite an extensive survey of schools existing at that time, with a particular focus on music accommodation in schools. And the result of that survey resulted in the publication of a booklet which was called Building Bulletin 87, and that's the green booklet there on the left-hand side. And a sister document to that, which dealt with music accommodation, was Building Bulletin 86, which was recently updated in 2010, in fact. Now, although these guidelines are very useful in helping with the design of schools, they were not mandatory. And so the Department for Education decided to take it one step further and to develop a much more comprehensive document, which not only included the requirements, but also means of achieving them, together with case studies. Some of these case studies were the ones that came from the survey that we'd done. And it was thought necessary to have a bigger team of acousticians developing this document, including acousticians with specialist knowledge, such as specialist knowledge on teaching facilities for hearing impaired students. And the whole document was edited by Professor Bridget Shields. And of course, that document is BB93, which was recently updated. And this document has had a profound influence on the design of schools since it was published. And I'm now very heartened to be in the consultancy world, where all the people I deal with in design of schools, such as architects, engineers, cost consultants, project managers, they're all familiar with BB93. And even contractors who, when I started, didn't know what acoustics was, are all now arguing about reverberation times in classrooms and noise limits from ventilation systems. So a great leap forward, I think, in the design of schools in the UK. Now, for something completely different, I became involved in a project with a professor of architectural history at Cambridge University, who was studying the relationship between music, acoustics, and architecture in Renaissance Venice. The study was based on 12 Renaissance churches, some of which were built by the famous architects of the time, such as Palladio and Sansovino. And the aim of the study was to find out whether the composers of the new music at the time, Renaissance music based on polyphonic music, composers such as Gabrieli, whether they were affecting the design of the churches to suit their new music, which in fact needed higher clarity than the earlier music. Or were the architects becoming aware of the requirements of the music and adjusting their designs to suit this new music? And I'd like to play you a short excerpt. So, first of all, yes, the highlight of the study was taking the whole of the choir of St John's College, Cambridge, to Venice, including the boy choristers, to sing in each of the 12 churches, and also to sing in various positions in the churches to simulate the arrangements that they would have had during the Renaissance period. And we did subjective assessments of each of these configurations using questionnaires, and we also did extensive acoustic measurements. And I just wanted to play a very short clip to give you an idea of the sort of things they were singing. This project was quite a tough assignment, I can tell you. The main outcome of the project was that there is some evidence that the architects were aware of the requirements, but only in special cases. And the most obvious example is in the most famous church in Venice, which is the Basilica di San Marco, which is where the Doge and his entourage worshipped. And the architect Santovino had built these special choir balconies in the chancel of the church, and you can see an example here with the choir singing from it, so that the sound quality in the chancel, where the Doge was seated, had the clarity that was required for performing this polyphonic music. Whereas in the nave, the other part of the church, it was much more reverberant, and so the congregation there didn't get the benefit of the acoustical quality that the Doge was experiencing. So the architects were designing high quality sound conditions for the people, the important people, but not particularly bothered with the rest of the congregation. I think things have changed, hopefully, a little bit now. So in the 20th and 21st centuries, of course, acousticians have had much greater influence on the design of space, speech and music. And I'd like to go through a couple of examples. This is a concert hall that we were involved in Melbourne in Australia. The client was very keen on having a traditional shoebox shape, but interpreted in the modern idiom. So all the ornamentations and chandeliers that you got in the 19th century concert halls had to be reproduced, but not using the same kind of decoration. So the architects lined the hall with timber, and they grooved the timber with a lot of swirling patterns, and they also modulated the timber to enable the sound to be diffused over a broader frequency range. Now, during the construction of the concert hall, the contractors, who were well aware that they were building a concert hall, decided to put on an inaugural concert of their own. In fact, they did it on top of the concert hall rather than inside the concert hall. And I just want to show you a short clip of this concert. You will have never heard it before, and you probably will never hear it again. So, that's the completed hall ready for the proper concert. And you can see there the kind of grooving patterns that the architects had put into the walls, all under strict kind of code that's supplied by the acousticians to get the correct depths and the distributions and the modulations and so on. And you can even see there the chandeliers that were reproduced, mimicking the 19th century type chandeliers. The hall's been open now for 10 years. It's been very well received, and it was voted the best recital hall in Australia following an independent survey. Now, the main rival in terms of concert hall design to the shoebox shape is the Vineyard Terrace, or the arena type concert hall. And we had the opportunity to design one of these for the city of Krakow, who wanted a 2,000-seat concert hall. And this is a 1:50 scale model of it, where we worked closely with the architects to develop all the surfaces to provide early reflections for clarity and early lateral reflections for envelopment. But the important thing about the design of this hall, which is rather different from the traditional Vineyard Terrace Hall, is that the traditional Vineyard Terrace Hall has seating all around the orchestra. And there are quite a number of people now who think that the acoustic quality of the seats behind the orchestra are less good than those in front. And in some Vineyard Terrace concert halls, up to 30% of the audience can be behind the orchestra. And this was avoided in this case, as you can see here, as all the seats are in front of the platform, and so we don't get this problem in this design. I'd like to take you on a little tour of this concert hall. So this was one of the early acoustic concerts with people assembling there, and you can see the tiers of the terraces, a big orchestral reflector to provide the orchestra with feedback to help them play in good ensemble, and then also the seating, which was carefully measured by the Bill Davis method, and quite a sophisticated arrangement of platforms, so the orchestra can place themselves in whatever orientation they want to. And in 2018, this hall was named after the famous Polish composer Krzysztof Penderecki. It's called Krzysztof Penderecki Auditorium. Now, in 2019, I and a number of colleagues left Arups and formed our own acoustics team at Rambol, and we're now celebrating our 10th anniversary next month. We're around 20 strong, and we continue working on architectural and building acoustics and environmental acoustics. And a recent project that we completed was a new opera house for Grange Park Opera, where the client wanted a traditional opera house after the Teatro della Scala in Milan, but suitably scaled down with 700 seats. So the seating follows the traditional horseshoe shape, and the roof is a simple pitched roof over the front stalls, but then as the roof follows the curve of the seating, it forms a shallow cone. And we did have some concern about focusing occurring from these curved surfaces. And so doing an analysis on this, we found that focusing was occurring between the curved cone of the ceiling and the balcony fronts, and was located mainly in the rear stalls, and the amplification in some of the seats was up to 10 decibels. So we also looked at the delay of the reflections, and the delay was between 45 and 60 milliseconds, so not particularly late. These reflections would generally be integrated with the early sound. So it was uncertain whether this focusing was going to be detrimental or beneficial. And so we took a risk, and we didn't introduce a lot of diffusing surfaces to see if the acoustics would work out okay. During the inaugural concert, which was attended by a number of critics who always seem to be keen on attending the opening of new opera houses, we were keen to see what the reports were like in the press. So Richard Morrison in the Times said, its acoustics are clear and supportive. Barry Millington in the London Evening Standard said, it's evident the acoustics are excellent. And Fiona Maddox in The Guardian wrote, immediate, lively acoustics. So we were very reassured by this, because we were worried that it might go the other way. So no detrimental effects were reported. And some critics commented that the singers' voices were coming over loud and clear, and that the balance between the singers and the orchestra was very good. So in this case, we were getting beneficial focusing. And I think a lesson that perhaps we can learn from this is as designers, we often get very concerned about circular geometries and try and avoid them or try and introduce a lot of diffusion. But we really ought to understand them in more detail because sometimes they can actually be a help to us. Now, 5 years ago, we were appointed by South Bank Centre to provide acoustic advice for the refurbishment of the Queen Elizabeth Hall and the Purcell Recital Room and the Hayward Gallery. Now, working on the Queen Elizabeth Hall was very interesting because it was designed in the 1960s by Hugh Crichton with a heavy support from Peter Parkin, who was my original mentor at Cambridge. And the side walls of the hall are covered in Helmholtz Resonators. You can see on the image on the right, there's a lot of slots there on the walls, and they're all Helmholtz Resonators tuned to 4 different frequencies. And it was interesting to look in the archives at Southampton University how these original Helmholtz Resonators were designed. And when we looked at that information, we found that each of the resonators had a polyurethane strip fixed to the neck of the resonator to enhance its absorption. When we came to look at them all those years later, there was no polyurethane strip in evidence. There was a little pile of dust at the bottom of each resonator. And so we had to make a decision as to whether we needed to replace these or not. And so we asked a master's student at South Bank University to do a study on it. And you can see on the left-hand side the reverberation chamber at South Bank where the student had replicated some of the resonators. And she came to the conclusion that the polyurethane strip was not really necessary. But what was a very interesting finding that she made was that by placing a curtain in front of the resonators, as you might do if you wanted a variable absorption system, that you not only got the mid and high frequency absorption of the curtain, but the curtains are also enhancing the bass absorption of the resonators. So you were able to get a very broad band absorber, which is a particularly useful device for variable absorption. And that's the completed auditorium, which has been open for a couple of years now and has been very well received. We continued our work with South Bank by advising them on the acoustics of the Royal Festival Hall in their continuing quest to improve the acoustics of that space. And at the same time, we were appointed by Sydney Opera House to do a peer review of the acoustic improvements that they're doing to their concert hall. Now, it's interesting that these 2 concert halls were built and designed around 50 years ago with the then available acoustic knowledge. And in both cases, the acoustics have ended up less than ideal. And this has led to quite a number of remedial measures over the years, which are still going on and have proved quite expensive. But today, we have the knowledge and the tools to design excellent concert halls. But we must be wary that we don't get deflected from our path by design fashion or architectural ambitions. We must remain on our clear path to achieve acoustic excellence. Now, the Institute is playing a very important role in this respect by holding a series of conferences on auditorium acoustics which date back to 1992. These conferences are held every 2 to 3 years at a location where a new concert hall or opera house or other auditorium has been designed. And they could be anywhere in Europe. And last year I chaired the conference at the new Elbphilharmonie Concert Hall in Hamburg, which was attended by nearly 200 delegates from around the world. And the delegates had the opportunity of listening to a concert in the hall, which led to some very lively discussions about the acoustic quality of that hall and also about how designs should be developed for concert halls in the future. So this is a very important benchmarking process that the Institute holds, which brings together acousticians from around the world, both researchers and practitioners, where they discuss or appraise the latest acoustics of a hall and then develop concepts and ideas for ensuring that our concert halls in the 21st century achieve acoustic excellence. So I shall end there. Thanks very much.